Okay. All right, let's begin. Let's begin. We're moving on to the new chapter, normal distribution. Last example, and then you got one more chapter, which is sampling. So this is your second last chapter, and this is an example of a continuous random variable. Just like you did discrete, you then learnt binomial as an example of a discrete. This is exactly the same, still follows everything that you learnt about continuous, about the area under the curve is the probability, and how do you find expected value and variance exactly the same way, no difference. Okay, now it's just a specific example. A specific example of what makes it a normal distribution and what do we know about normal distribution. And so there's actually a lot of slides on this one today, but the theory is very simple. Okay, I'm going to try to give you as much in-depth explanation as I can because it's only one thing you have to take out of it and you totally understand it. That's it. That's the difference about the question. I'm going to show you 3 past exam questions so you could see if you understand it, it's just a symmetry property. If you understand that, that's it. Okay, there's nothing more, nothing hard. It's all calculator work at this point. Okay? All right, so let's have a look at what a normal distribution is. Let's think about, so this is your normal distribution graph. Okay, it has a curve. This curve is modeled by an equation, and this is the equation. Now, you're not meant to know where this came from. They just figured out, they typed this in, they were like, oh, hey, look at that. This gives you what they wanted. Okay, they wanted a specific, and a couple of properties here. This is why I want to talk about the properties of what we call, this is a standard normal graph. Why is it special? Because you'll notice that the mean, which is the peak here, the mean is equal to 0. And they also designed it such that a standard deviation is 1. That's what makes it a standard normal graph. Now this equation here is just describing that. That's it. It just describes that this curve, f of x, is what you see there. This bell curve is symmetrical, and the area under the curve is 1, and it's above the x-axis. This is a continuous random variable. It's a curve, and it fits everything we talked about what a probability density function is. That's why it's nice. Okay, so if we can model things in life such that it fits under this curve, if we can translate our data so that it fits under this curve, we can use continuous random variables to answer questions, to find the chance of something occurring. But the first thing is it has to model under a normal distribution. It has to model under this curve first. Okay? Yes, Tom? This is the general. This is the general idea. Okay, and so I want to put my emphasis on a couple of things here, and this is where I'm looking at. You see, where we're looking there is the primary issue of why most students find this difficult to understand. If you understand what I'm saying, it comes out just from there. That's the point, and I'm going to try to keep reiterating so you can see the difference here. We call this a standard normal. This is what we love. This is all we know. They know this curve, and this is the curve they love. It's symmetrical, mean is 0, standard deviation 1. That's why it's beautiful. Okay? So you found the area under the curve. If you find the area under the curve, you found integration of this equation. If you found integration of f of x between negative infinity to infinity dx, this will equal to 1. And currently, f of x is greater than 0. And so therefore, it fits in your 2 conditions and makes it a PDF function. So it's a probability density function. This curve is beautiful. So the problem is, well, in real life, it is not like this curve. In real life, your mean is not 0. In real life, your standard deviation isn't 1. So the goal is to make everything so that it moves back so you can relate it back to a normal distribution. That's the goal. And this is where this comes into play. Okay, so what I'm writing here, this arrow, this focus on is this transformation. Okay, so this transformation, if we actually go back using the transformations that we've learned back in chapter 3, this is the transformation. And if I asked you to read the transformation right now, you would tell me this is a translation of, this is a translation of your mean units to the left or right, so it's a translation. So what that tells me already is the mean moves left or right, moves the graph left or right. The standard deviation in this case tells us the dilation. What does dilation do? It stretches the graph. It makes it thinner or wider. That's what we know. So they say it's a dilation factor of 1 on sigma, which is 1 over your standard deviation from the y-axis, because that's what this is. From the y-axis, so moving away from the y-axis by a factor of 1 on sigma. We know that from transformations. And then it's also a dilation of factor sigma from the x-axis. Yeah.
What's the original equation?
This is the original equation. Okay. That is like the so this is the original equation in the sense that if you had a mean, now mean is 0, so if this is 0 and this is 1, then you'd get e to the negative half x squared. See what I'm saying there? And that means this is 1 as well. So your original equation would be 1 on root 2 pi. See what I'm saying there?
Yeah.
Okay, so if you change your standard deviation, you change your mean, it changes the graph. But you have to understand that the mean just moves it left or right. And the standard deviation, which is the spread of the data, just makes it wider or smaller, thinner. Okay? Now let's focus on this. This is just the theoretical part. It's part of your textbook, but I've tried to break it down so you can understand what they're trying to say there. Okay? So, now that we know this, what I want you to pay attention to is this part. When you're dealing with normal distribution in the chapter, you'll be referred to what they call Z values. When they say Z values, they say Z equals to X minus mu on sigma. All they're really saying is they're just, instead of writing this entire thing, they just called it Z. And they said if you drew a graph, a normal distribution graph where this is f of x and this is your Z axis. So they're just saying change the graph so that you have this. 1 on sigma root 2 pi e to the negative half Z squared. That's all they're doing. Okay, where Z is your x-axis. Why you want that is because back in the day they had to have a standard, just something that is easy for them to calculate, and they've just called Z as your x-axis as transformation. Now back in the days when I did it, I didn't have a calculator where it calculated the probabilities as you did. We had to use Z tables. And Z tables, it would have your x values, doesn't matter what x values, it corresponds to a probability and it corresponds to the Z value here. Now what is your Z value? So when I say Z value of 1, the nice thing about this is when you say Z of 1, it actually means standard deviation of 1. That's why it's beautiful. It's beautiful because when I say Z equals 2, that refers to 2 standard deviations from the mean. Now if you remember what I talked about in binomial chapter 14, I said that 95% of the data comes from the mean. How do you get out of this? Okay, comes from the mean minus 2 standard deviations and mean plus 2 standard deviations. This will give you approximately 95% of the data. Okay, the nice thing about this is I can then tell you just from the graph here that if it's a binomial, normal distribution, I can tell you that from here to here, if we found the area, it's approximately 95%. So what does that tell me? That means that the two sides have to be 2.5%. Because 2.5 plus 2.5 is 5. 5 plus 95 gives you 100%. Okay? And because it's symmetrical, that's why it's nice. That's what we love. So the Z values represented your standard deviation. That's why we love it, because each standard deviation was 1. And now you change your axes to Z values. That corresponds to the standard deviation. That's why we loved it. Okay? Now, the issue is, as I said, in reality, not everything standard deviation is not always 1. And your mean is not always 1. So that's why in this chapter, this whole chapter, normal distribution, you're focusing on, depending on their data, they'll tell you either like IQ mean is 100, and they say that, like the standard deviation is, one standard deviation is like 6 points. Okay? And then they want to find out what is your Z value, or they might say probability of Z greater than 1. And a lot of students find this difficult because they don't understand what Z greater than 1 actually means. But if you understand what I'm saying there, they're just saying Z greater than 1 refers to the x-axis, which is your Z values. When they say probability of Z greater than 1, if you knew the mean for IQ was 100 and you knew standard deviation was 6, all it's saying is find out the area under the curve, because probability is the area under the curve, z greater than 1, this is where 1 is, so greater than 1 is this area here. And with back then, we had a z table where they already calculated this particular graph. They've broken it down into its z values, so you can actually refer to it, and your calculator will tell you. That's why I'm saying this whole chapter is all calculator based. All of it, in terms of understanding, is just theory, and you just apply it in your calculator. That's why it's not a hard question, it's not a hard chapter, but it is hard for students to understand because of the transformation that is applied here, the theory behind it. Okay, so if you didn't understand what I was just saying before, I was just saying, they love this curve, this is what they want. The reality is, we don't have that curve, so we're going to try to change it back to that curve. Okay, so how do we change it? I'm going to show you in the next slide. Okay, and that comes from this idea. Z equals to x minus your mean divided by standard deviation. That is the transformation to bring it back to its original graph. Okay, that's your goal. So let's have a look. In terms of, because we know symmetrical, these are some basic theories. From, if they said probability of negative infinity of x to infinity, they're just saying find the area of the entire area under the graph. Well, we know it's a PDF function, so of course it equals 1. Done, too easy. You know that because it's a PDF function and it's symmetrical, that means if I shade it up to the half point, well, of course it has to be 50%. That's why it's 0.5. That makes sense. Whether it's from negative infinity up until mu, or whether it's from mu up to infinity, it doesn't matter. It's still half the data. That's why this is 0.5, and that is also 0.5, logically. Okay? Now, this is where I'm talking about. This is, we love this. Okay, this is our graph. We love this graph. This is our standard normal. We call this the standard normal. This is our real life data that happens to fall under the distribution that it is normal. Okay, but notice the difference. The mean for this is 100. The mean for this is 0. We love this. We don't like this. So how do you change this? Well, naturally, if you're at a mean of 100, the only way to get back to 0 is subtract 100, which you're moving back to the left. You see, you're just doing a transformation. You're moving the graph to the left, but also notice that it's thinner. Standard deviation is different. So how do you move it all back? It is just this idea. That's just moving back the graph to 100 back. And then, see, like, if the mean was 100, if x was 100, well, you can see already, if I subbed it back in here, this will make it 100 minus 100 over 15 squared, which is 0, which is what I want. That's what I want. I want the mean to be 0. That's what it's doing. It's just moving this graph. The whole idea is, and the whole idea is just to change the graph back to what we call the standard normal. So I'm going to write again. This is your standard normal. This is reality. Reality is normal distribution. Okay? Now, because it's a normal distribution, we know we want to move it to this point. Okay? We can say that, okay, that means it's sigma equals 15, mean, which is 100. Okay? We can now use this to get out my z value. So when I say z value of 1, okay, z value of 1, this is just saying, what does that correspond to reality? And this is just saying 115 is exactly the same coordinate or position in my standard normal as 1. Now, how do I get 1? Same thing, 115, which is my x value, minus my mu, which is 100, divided by my sigma, which is 15. That's 15 on 15 equals 1. So this is my z value. This is what I said. I said z equals to x minus your mean divided by your standard deviation. This is just a transformation. Okay, it's nothing special. It's not a formula in any way. It's just a transformation. You're just looking at your transformation. You're just trying to say, all right, what does 115, if we were to, dilate it and translate it, what would it correspond to in terms of my standard normal graph? Okay, because this is all we know. We've done all our calculations, we've done all our probabilities, everything. There's a z table out for this, but it's only for this. There is no x value table because everything in life changes. So you can't predict that, but what you can do is if you can model it so it fits to this, you can predict it. That's why we like it. So we love the z value. We're trying to change everything from here to here. Okay, and that's the one thing I really need you to understand, because then it makes sense when you're reading the question, you know if you're finding z or you're not. A lot of students will get confused because they'll use the functions in your calculator. Everyone can use a calculator, but you have to understand what you're doing on the calculator. Okay, when you're doing the inverse normal, you have to understand why is the mean equal to 0 or why doesn't the mean equal to 0. Okay, you have to understand, are you working with your x values or are you working with your z values? That's the key difference. Okay, so having said that, I tried to summarize. Oh, no, that's not it. How do you... There we go. Okay, so normal distribution is a type of probability density function. We love it. It's symmetrical. It has a mean of 0, standard deviation of 1. Area under the curve represents the probability of distribution. It's all great. Therefore, everything that I've taught you, standard in terms of 95% of the data, it is 2 standard deviations above or below the mean. Now, this is called a standard normal. If they say convert it to standard normal, if they say this is a standard normal distribution, you got to know they're talking about z-axis. If they don't say standard normal, then you got to assume it's this. Okay, so this is x-axis, this is z values. This is to convert x values to z values. How do you convert it? Z equals x minus mean of a standard deviation. That is the transformation to bring it back to this. Okay, that's all you're doing. So, now that you understand that's the concept, it's just a transformation of z, x minus your mean over the standard deviation. That moves your current graph to this particular graph. That's all you want. You're just trying to move it to this beautiful graph that you have. Okay? This one we don't know. Okay, so this is what you've been dealing with. This is just a function. And how you find the expected value has always been the same. Expected value for continuous random variable is, you know, negative infinity to infinity of x times your f of x dx. That's what we learned in chapter 15. Yeah? That's how you'd normally find it. Now we're just trying to move it over here so that it's by default, mean is 0, standard deviation is 1. Okay, that is the goal. Now, I'm just putting this box here so that you can see that you don't get confused. When they say probability of x less than or equal to a, and they write this, they're just asking a and this, how do they correspond to each other? Just like I showed you, 115, so probability of x less than 115 is exactly the same as saying probability of z less than or equal to 1. Because this is where 115 is, that's where x equals 115. We just want to know if we translated this to a z value or z function, where is it? And 115 corresponds to the 1 which I showed you before. So when I say find the area of x less than 115, that corresponds to the area less than 1. Why do you want to know that? Because like I said, the z tables will know what probability of z less than 1 is. They actually have a table, full table, that will calculate, would have calculated already for you what z less than 1 is. But you don't know this. You see, if I ask you probability of x less than 115, we don't know. There is no table for that, but because we can refer it back to this table, that's why we know. That's why you're using a calculator. Okay, you're not going to do what I did. We don't go through z tables anymore. You type in your calculator and it will find that value for you. Okay, so that's all you need to understand. That's the one concept I need you to understand. Okay, that is just a transformation. Your goal is to move x to z. Right? Now, and just to reiterate again, if you weren't listening, the mean moves left or right to translation, and standard deviation is just the width of the graph. Okay? Yes, Roberto?
So we move x to z and then do we have to integrate?
I'll show you how to do that. Yes, you normally would if you were to do it by hand, but you won't be doing it by hand in this course. You're going to do it in a calculator. Yes. Yes. Okay? Now, just to reiterate, just so that you understand what I mean, this is when you change the mean. So if mu2 is greater than mu1, clearly it just shifts your graph to the right. Okay? So the width stays the same, just moves to the right. What happens if you change the standard deviation? I said that's a dilation. So if I said that mu2 was greater than mu1, how does that change things? Now you got to remember, standard deviation is the width. So if it's greater than, obviously it's a bit more flat. If it's smaller than, obviously it's thinner, because the space for you to make is much thinner. The space that you have to consider that is 95% is obviously thinner, so that's why it's higher. So logically, this is what they're trying to show you here. They're just trying to say if this sigma 2, which is the width of the second graph, which is the red one, If it's greater than the first one, of course, it's wider. You see, like it's much wider. Standard deviation is much wider. See that compared to this one, the standard deviation is much smaller. So of course it's thinner. Okay? So that's what it does. It's a dilation. And remember, if you stretch it horizontally, you also stretch it vertically. There's a dilation of factor sigma from your x-axis and a dilation of factor 1 and sigma from your y-axis. That's why it gets thinner. Okay, it's just a transformation. It all goes back to this one concept that I was talking about. This is all you had to understand. That's all you had to understand. For chapter 16, normal distribution, this is the only one thing you have to understand clearly what this is really talking about. Okay? The function is a beautiful function, that's it. Okay, it's just a beautiful function, we love that. And why we love it? Standard deviation is 1, mean is 0. That's why we love it. Okay? Now, a couple other things just so that you know this is for 16b. So I went through 16a just now, the theory about it. 16b is just getting you to memorize this. So you know this from previous chapter. Now you know that one standard deviation to the right or the left is about 68%. 2 standard deviations, 95. And then 3 is about 99.7. These are 3 things you must remember because they will come up as part of your exams in a multiple choice section. If they said, you know, find 99.7, you had to understand what they're assuming. They're assuming that you understand it is 3 standard deviations to the right and left, and that's the difference. Okay, so these are 3 properties that you have to know. So previously you only had to understand the first one. Now there's 3. Okay, so just going back, just those 3 you have to remember. 68 is 1, 2 is 95, 3 is 99.7. Write it down. That would be something I would write on a cheat sheet just in case I forget. That's a property I need to know. Okay? Now, just reiterating what I'm saying before, when you say probability x is less than or equal to mean minus alpha, if let's say mean minus alpha is here and I say x is less than, well, it makes sense that I'm talking about this area less than. If I wanted to talk about greater than, then this would be probability of x greater than or equal to mean plus alpha. Okay, so it's just a notation. I'm trying to get you to understand notation first. Okay, notice that this is x, not z. That's key. Okay, let's do an example, a very quick example so you can see what we're talking about here. So, suppose that z is a standard normal. See what I said? That I said the only thing you have to pay attention to is if they told you it's standard normal or it isn't. Because if they say it's a standard normal, your immediate assumption, this is a textbook, that's why they tell you, but your immediate assumption is mean is 0, standard deviation is 1. In your exams, they're not going to tell you that. When they say standard normal, they're implying that. You have to understand that. Standard normal means mean is 0, standard deviation is 1. Okay? So, when I say that and it says find the probability of z being between -1 to 2.5, I want you to visualize this. Everything's all visual. This is your graph. Normal distribution. Mean is 0. When it says standard deviation of 1, so this is -1, that's 1 standard deviation. 68% of the data stays in this region. Okay? But what they're asking now is they're saying from -1 to 2.5. I would expect that it's greater than 68%, logically. Okay? Because if this is 68, then obviously including this region here has to be more than 68. Okay, now how do you calculate this? Yeah, you can do what Roberto was asking. You can do from -1 to 2.5 and you define your function. And what is your function? The standard normal function was 1 on sigma root 2 pi. You don't have to memorize this. They normally don't get you to do this, okay? But it's x minus mu on standard deviation squared. If you define that function and then you tell them mu is 0, standard deviation is 1, and you sub it in and did an integration, yes, that will tell you the area. They'll tell you the area and the probability. But you don't need to do that. You did have to understand the theory. But in order to answer the question, all you're going to do is put in your calculator. So here, how am I going to put in my calculator? All I'm going to do is this. This is found in your, if you have a calculator on you, menu probability distribution, just like your binomial. The only difference is it's normal CDF. Why CDF? Because you're calculating a region. You're not calculating for a specific point. You're now calculating for a region. That's why you're doing CDF. Okay? So, it's not PDF. You've got to understand the difference PDF and CDF. CDF is cumulative data. That's what C stands for, cumulative data. Okay? So, this is what it looks like if you got into that section. See, all I'm doing here is if I understand what I'm doing, I'm just summing all the areas. Lower boundary was -1. Upper boundary was 2.5. This is where a lot of students confuse, and I don't understand that you're not meant to confuse yourself here. If they told you standard normal, it's implied. It's implied that your mean is 0 and your standard deviation is 1. You didn't have to guess that. Okay, that's your Z values. So if you type that all in your calculator, you press OK, this comes out as 83.5%, which makes sense because I did say it had to be greater than 68%, and it is. Okay. Second one, if you visualize this, same thing again. This is a standard normal graph, and all it's saying is if the mean is 0, greater than 1. This is where 1 is. Greater than 1 is that part there. Now what you can see is if this is 50% and whatever this region is, this must be much less than 50%. Probably less than 60. It's a small percentage, logically. Okay? So when I get my answer, this is what I mean. Evaluate your answers. Does it make sense graphically? Because sometimes students put an answer down. I'm like, how does that make sense? If you drew the graph, you'd know that can't be it. Okay, so if I think about it, I'm like, okay, it's got to be less than 60%. It's probably, you know, something maybe in the 40s, 30s, or even 20s. Okay, let's do it. Same thing. The only thing I changed was this 1 to infinity, because that's what I said. It was from 1, and I just wanted this part. I just wanted this area here. So that made sense that I'm saying this is probability of Z greater than 1. Pretty easy. Okay. It's much easier now because you guys got a calculator, you can do that. Back then I had to convert this because we only work from left to right. So the only thing we had to do was we had to change it to 1 minus the probability, or you had to work out, in order to find the area, you had to find out this area first, and then you subtract it from 1 to find out this area. Okay, so we had to do 1 minus probability of Z less than 1 because the table's only ever calculated from left to right, never from 1 onwards. It's always from negative infinity up to a certain point. So that's what we had to do back then. And you are still going to be required to do that. You have to show that you know how to do this, and that's in the later exercises. Okay? But the theory is very simple. Okay? So, let's do this one. Now, so I taught you how to find the probability values. Now what you have is the opposite now. See, now they don't tell you what K is. They tell you what the probability is. If you visualize this, it's not a hard problem. Think about it. It's not a standard normal. Notice it's not standard normal. You got mean 100, standard deviation 6. So I can draw a graph and go like, okay, it's probability distribution, normal, so it's symmetrical. I know it's at mean is 100, standard deviation is 6, so that's 106, and this is 94. Okay, 68% of the data fit between 94 and 106, logically. Now, all they're asking is, X is less than or equal to a certain number and is 95%. Now, I don't know what K is, but I know K has to be somewhere in this region here. Because K, if this is halfway, this has to be 50%. Up to here is 50%. The 95 has to be somewhere over here. See what I'm doing there? I'm trying to find that K value. So, how do you find out that K value? You can do, you know, your integration, negative infinity, up until K of f of x dx equals to 0.95, and you can calculate it by hand. Yes, you can. The problem with that is the curve is going to be an ugly curve, and we don't know how to integrate that. So that's why you use a calculator here. And you'd say, all right, to find that K value, you have a function called inverse normal. It's exactly in the same area. Menu, distribution, probability distribution, and then inverse normal. What that does is it just finds out that X value for you. So this is what it looks like. There you go. They'll ask you, well, what is the area? Well, you know it's 95%. They ask you, what is your mean? We know it's 100. They ask you what your standard deviation is. You say it's 6. Voila. Okay? They just tell you. But remember, what does this tell you? This just tells you 95% of the data from the left to the right. You got to remember, from left to the right, 109.8. So what are they saying? If I drew out the graph for you, mean was 100, 106, and 94, this is what your graph looks like, true? All they're saying is at 109.8, they're just saying this area is 95%. You have to remember it is from left to right. This only calculates left to right. That's what you must understand. The reason why I'm emphasizing left to right, because in your exams, they're not going to make it that easy. Instead, they're always going to ask for the greater than. So that means when you type in this area, you have to understand that because they might say something like this. Instead of saying x less than or equal to k, they'll change it. This makes a difference on students. Instead of saying less than or equal to, and I said greater than or equal to k, is 0.16. What kids would do is they put in 0.16 here, they put 100, put 6, and whatever comes out, they think that's the answer. Why is that wrong? Because all that tells me is this. Graphically, you're saying 16%, this is 16%, and they're saying this is mean 100, standard deviation of 6, so 94, 106. They just calculated the value down here. But I actually asked what value would give me greater than, and it gives me 16. See the difference there? This one gives you a value less than the mean. This one gives you a value greater than the mean. And that's why students normally screw up, because they're not visualizing it. Okay, Malshi? Okay, so because when they say x is greater than or x, so they say probability of x greater than k equals to 0.16, hypothetically, if I said that, okay? I want you to visualize this. Every time they give you a normal distribution, draw it. It doesn't have to draw. Okay, at this point, all I'm saying is, if I just go back, if I just remove everything, all I'm saying is this. If I say probability of x greater than or equal to k is 16%, visualize this. I'm just saying my mean, I don't really care what my mean is. The point is, it's just saying greater than k, so k could be any point. K is at some point, and they're saying the area under that curve, which is the probability, is 16%. That's all they're telling you. They're just saying this right here is 16%. If they said less than, if I said less than, so if I said x, whoops, if I said x is less than or equal to k, then I'm talking about this region. But it makes sense the probability can't be 16% at that point. Okay, at that point, it obviously has to be more than 50. So they might say this is like, I don't know, let's say 78%. Okay, and the reason why this is easy to figure out k is because when you type in your calculator, this only ever works from left to right. That's what I wanted you to pay attention to. That only tells you what k value. So when they say 109, that only calculates from left to right. So visually, this is all they did. They just said k, this is k, we don't know where it is, but we do know the area under the curve is 95%. And they said it's less than. So because it's less than, I can say, oh yeah, this is less than. This is all the area less than. So that's why when you do the inverse norm in your calculator, it will calculate the value and say, oh, it's 109. Because they're just telling you that value has to be 109.86. If you knew the mean is 100, standard deviation 6, they know from left to right, you'd have to be at 109.86. But if I changed that question and I said, I want it to be greater than k and I want it to be 16%. You see, if I typed in my calculator, and I wrote this, 16%, all they're going to calculate is from left to right. So from left to right, this is my graph. From left to right, 16% will be about here. That's 16% from left to right. And that tells me this value. But that wasn't what I wanted. I wanted greater than k. Greater than k. So it had to be, k had to obviously be over here. And that's 16%. Why isn't it this region? Because that's clearly bigger than 16%. So it had to be this k value that you're looking for. This is the k value. And this k value is obviously bigger than the mean, logically. Okay? Does that kind of make sense? Yes, no? All right, okay. So inverse normal only calculates from left to right. And notice what I'm doing here. See 109.869. What did I change? I changed the mean to 0, changed standard deviation to 1. What is this value? Yes, that's it. It's just a z value. All I'm saying is your normal graph, if it was a mean of 100 at 109.8, that's equivalent to a standard graph, mean of 0, and it's at 1.6. That's all it is. This is the transformation. That 109 is equivalent to 1.6. That's it. Okay, because they refer to the z values. They only have a z value table. That's what they love. And that's literally all of the theory for normal distribution. You're just playing around with the equations right now. Okay, so the main one that I want you to practice is not exercise 16A, not 16B, but 16C. It touches this topic, and that's the only one that goes on to the exam. Okay, now you can have a go with these questions. I've got the solutions, but I'm more interested in, if you understand the theory, I want you to do this question. So 68 or 63% of students got this correct, and the next two, it will change dramatically because students don't understand what they're doing. And it changes dramatically, it drops down to 37%. Why? Because they can't visualize, they don't know what the area equals to. You have to understand it's just a z value. Okay, so I want everyone to give this one a shot. You should get the answer if you understand what I'm saying. It's the next two questions that I'm interested in. Okay, have a go with this one. I'm going to give you a bit of a time. That's make it 2 minutes so we can go into the next two. Okay, 2 minutes. Let's go. Normal distribution. Mean 14. Standard deviation 2. Find the z value, random z value. Probability is greater than what? Yes? Why not? No, it's still like if it's 94, and standard deviation is 6, then you got x is 94.
I had it on all night and I woke up and it was still red. It's a mini freak out. Thank you.
How was that when you were being here? Yes, you may.
I think I'll try to give it right here.
Okay.
Okay, excuse me, just listen up. Those for specialist maths this afternoon, we are entering at 1:20. We are entering at 1:20. Be outside here at 1:20 so I can let you in at then. Okay, there is 5 minutes reading time for the SAC for today and for tomorrow. No books, just writing implements, calculator, and please leave mobile phones in your lockers. Thank you.
Nice. All right, Year 12's listening. Shh, shh, shh. Just for this question, just in case you didn't know how to do it. Same thing again. Notice they didn't tell you the standard normal. They told you the mean is 14, standard deviation is 2, and they just want to know when x is greater than 17, what is that corresponding to? That's all they're asking. So if I said probability of x greater than 17, what is that in terms of z value? That's all I'm asking. Graphically, this is what you have. Mean 14, standard deviation 2, so this is 16 and this is 12. That's all you know. Now we're asking at 17, what is that corresponding to 0 and 1? That's all you're asking. So how do you find that? It's just a transformation. What's a transformation? Bam. Just the one concept. Transformation z equals x minus mu over standard deviation will tell you 17 is equivalent to 1.5. That's all it's saying. It's equivalent to 1.5. That's all it's telling you. Okay, and so therefore you can answer the question. If you want now greater than, see, this is what I'm saying, you got to be careful, greater than or less than, because it's greater than 17, greater than 1.5, it's also the same as the probability of greater than 1.5 is exactly the same as the area of z less than negative 1.5. It's symmetrical. Okay, for the z value, symmetrical. If you go 1 across, you go 1 across. Go 1.5 across, you go negative 1.5 across. Okay, that's why it's good. Now, if you have enough time, do look at it. I've got another 2 questions. The main one is this one. A lot of students struggle with that. Most kids can do this. That one. Okay, and same thing. Don't look at the answers right now. Don't look at them. And same thing with this one. Most students struggle with that one. Same concept. It's the part B, 2 marks. If you understand what I'm saying, it is very straightforward. Okay, look at the PowerPoint. Have a go at them. That's very key. Exercise 16C. Priority for your exams, not for your SAC, for your exams. Priority 16C. Okay. Focus on that. Thank you. The bell's just about to go. You guys can pack up. Thank you.